Hey y'all, so I wanted to put together a video that would go through the resistive forces that we did in class last time. And I understand that when we went through it, we did things from beginning to the end, and it was very, in some ways, confusing on what was going to be expected of you and what was not. So what I'd like to do is I'm going to go through it again, but this time I'm going to try to make it very, very clear with what is expected for you to know and what are things that maybe you don't need to know at this point in time. So the same process I'm going to go through today, but I'm going to do what's expected of you on this whiteboard right here. And then at some point, we are going to shift over to the other whiteboard and we'll talk about some other things that I want you to see, but you wouldn't necessarily be asked to replicate yet at this point. All right? So what is expected? Well, we do want to understand that the resistive forces depend on velocity, right? That the faster you're going, the more resistive force that there is. And so we did talk about that. We said the resistive force is proportional to and opposite the direction of your velocity, right? So that you should be comfortable with. You should be able to use that in conjunction with any of your other Newton's second law situations, all right? The K, remember, is just a constant. It takes into consideration surface area, size. It might take into consideration the density of the fluid, right? Lots and lots and lots of things that are contained in that K there, right? The fluid is more dense, you expect more resistance. You have more surface area, you expect more resistance, right? A variety of different things that could be in there. As you get further in your physics/science/engineering journey, you may get to the point where you can actually do some more things with that K and put more variables in there so that you can actually do some other things with it. For now, we're just going to leave it as that, okay? Partially because we don't have as many mathematical tools as we would like yet, but also just partially because that's the level that we want to do it here. Now, one of the things that we talked about last class is we started talking about, well, how about this idea of resistive forces as in terminal velocity, right? When we have an object that is being dropped, right? Initially, it starts with a velocity of 0, and it has an acceleration that is equal to g. Now, as it falls, it gets more and more velocity. Now, as the velocity increases, that means the resistive force is going to increase. At this point, because the velocity is 0, if I were to do a free body diagram, the free body diagram would have the force of gravity down and no resistive forces, because remember, resistive force depends on velocity. If the velocity is 0, then there's no resistive forces. But as that object falls, then we would get to a point down here where we do have more velocity. What would the free body diagram look like? Well, this one, it is dropping, but we don't have any velocity yet. I talked about that. So this one, we have the force of gravity, which should be about the same, okay? But now we have a little bit of resistive force, right? Now that little bit of resistive force should mean that my net force is less than it was before. And so therefore I'm going to have a smaller acceleration. So my velocity is going to have some value now, okay? It's not going to be 0, so maybe I just go is not 0, and my acceleration is less than g. Now, I'm talking about the magnitude of the acceleration here. So if g was 9.8, the acceleration would be less than that. If you're saying negative 9.8, then something between that and 0, obviously. The magnitude is less than g. Now, as it goes faster and faster, this force continues to get larger and larger. And as that force gets larger and larger, then eventually you will get to this point where the resistive force and the force of gravity are equal to each other. And at this point, it doesn't accelerate anymore, right? So at this point, you have your largest velocity, which is where your velocity is equal to your terminal velocity that we often call it, and the acceleration is 0 because the forces are equal. Now, because the acceleration is 0, the velocity doesn't change anymore, and so therefore the resistive force doesn't change anymore, and we are now caught at this standstill. Not standstill because it's still falling, but it's not changing its motion anymore. That's why we call it the terminal velocity. That's that final velocity. So we can see that. We've talked about that before. Now, what does the equation look like? Well, if we go sum of the forces equals MA. The sum of the forces is, now I'm going to do this slightly different than what I did in class because we wanted to end up with the negative and the exponent, and we didn't do that because of the way that I set it up in class. So to get the negative and the exponent, we're going to call down positive. So as it falls down, that will be a positive value. So my FG is going to be positive. And then I'm going to go minus F resistive forces, and that should equal MA. Okay? Now we know the force of gravity is mg. The resistive force is kV, which should be equal to MA. All right? Now, at this point, all of that you should be comfortable with, right? None of that is too weird. None of that is too crazy. This is all makes sense with what we've learned about Newton's second law. I haven't even used any calculus yet. Okay? Now, the next step, we're going to step over to the other whiteboard, okay? Because what I want you to see is, okay, well, how would we then get an equation for velocity? Now, I know some of you are like, well, that's easy. I just subtract the mg, I divide by the negative k, and bloop, I got it. But the problem with that is that your acceleration depends on the velocity. Acceleration's not a constant. So you can't just solve for v here, because you would still essentially have v on the other side of the equation. That doesn't count for solving for v. You need everything on the other side to be constants, or those other variables that you're measuring. They cannot depend on v. And so therefore, we're going to have to do something else with this. All right, so this is required. We're going to move over to the other screen now. All right, and so now we're going to do the calculus that will allow us to determine exactly what is the equation for v. All right, now ideally we would like to have an equation that is v with respect to time. So how is v changing over time with a not being there, right? Because a depends on v, which depends on time. All right, if that doesn't make any sense, that's okay. So what we did first is we said, okay, we know that a depends on v. Well, a is dv dt, right? So our first step is we're going to rewrite this as mg minus kv equals m, and then a is dv dt, right? That's one of the first things that we learned in this class when we started learning about calculus, is that acceleration is the derivative of time. Okay, the derivative of velocity with respect to time. So hopefully you're okay with that. Now at this point, I do need anything, we're going to do a separation of variables here. I need the things with v on the side with the dv, and I need the dt on the other side. Okay, now it's tempting to say, okay, well then let's just add kv. Now if you do add kv, you're going to add kv to this side. You're not adding it inside of that dv dt. And that is a problem because we want it to be inside so that we can actually take the integral later. All right, so we're not going to add the kv. Instead, what we're going to do is we're going to divide this whole side by mg minus kv. I'm going to divide this side by mg minus kv. Now I also, so divide by mg minus kv. I also want to get the dt away. I'm going to move that over to the other side. So I am also at the same time going to multiply by dt. Okay? Now hopefully you'll see that these will cancel out, leaving me with a dt on this side. And then over on this side, I'm going to have m over mg minus kv, and then it will be dv. Right? Now, with that, I'm now ready to take the integral. Now, I understand that this is not something you've done in calculus class yet. That's why we're over on this board. This will not be required of you yet. At some point this year, you should have the calculus skills that you can do that. But right now, I'm just showing it to you so that you can see where our final equation is coming from. You can see what we can do with the calculus. All right? So what we're going to do is we're now going to take the integral of each side. The left side we're going to take with respect to t, because that's what the dt is. We're going to add together all those dt's from 0 up to whatever that final time is, okay? This is going to be the integral of dv from our initial velocity, which if we're dropping it, the initial velocity would be 0. This technically could change if I started with some initial velocity, but I'm not going to. I'm going to go from 0 up to vf. Now, this is important because note that I made this positive. That is dependent on me deciding that down is positive. My final velocity should be downwards, okay? If you don't do that, then this velocity final ends up being negative. That's why some of the things when we worked it out in class, sometimes the positives and negatives didn't quite work out because sometimes the negatives were inherent inside of the variables and we just weren't seeing that, all right? So we're going to go ahead and do the integral now. Now this integral is a little bit challenging because we don't know how to do this specific integral, but what we can do is remember what we learned a couple of classes ago, the u substitution. Okay, so I'm going to make u equal to mg minus kv. That means du dv, so if I take the derivative of that, then I should just get negative k, right? Because the derivative of this would be 0, the derivative of that would be negative k. Then I will move the dv back over, and so I get du is the same thing as negative k dv. All right, so that can now be substituted back into my integral over here. So I will have the integral from 0 to the final time dt must be equal to the integral from 0 to the final velocity, which is terminal velocity here, right, of m over u, and instead of dv, sorry, I guess I needed one more step over here. So du over negative k is equal to dv. So for the dv here, I'm going to put du and negative k. I'll put the negative k right over here with my fraction. Okay? And so now the m and the negative k, those are constants, so I can pull those out of my integral. And once I pull those out of my integral, I should then be able to take the integral of 1 over u. All right? So I can do the integral of dt. The integral of dt is just t. So this is going to be t integrated from 0 to tf. That's going to be equal to negative m over k times the integral of 1 over u. Now, if you don't know what that is, that's okay. You just look it up on your AP equation sheet. They don't expect you to memorize all those integrals. They are right here. And you should be able to find right here dx over x plus a. So that's essentially dx over u, so that will be the natural log of u. All right, so we'll go times natural log of u evaluated from 0 to vf. And so now we can go ahead and put those numbers in. We actually want to put the u back in. Okay, when you do use substitution, there's actually two ways to do it. One is what I'm doing, which is you put the u in and then you don't change these. These are supposed to go into the v. And so when I get to the end, I've got to put the function back in for u so that I can put these in for v as is proper. The other way to do it, which you'll find out in your calculus class, is that when you change this to u, you can actually then change these so that they're in terms of u instead of in terms of v. All right, don't worry about that right now, but I just want you to understand there's two different ways to approach this. I really probably shouldn't include these here. I generally will just not worry about it, and I'll put the v, that extra function, I'll put that back in for the u. And when I put that back in for the u, then it will actually be easier for me to work with. It's easier for me to think about, to not have to change the limits of my integral there. Okay, so let's see. So this is going to be t v minus t0, which is 0, so that's just going to be by itself, equals negative m over k times, oh, I need to put in the u. U is mg minus kv, so I'm going to put that back in here. So let's just go ahead and put that here. So mg minus kv, and that's from 0 to that final velocity, whatever that velocity is. So m over k, so I'm going to put the 0 in first. So if I put the 0, I'm going to put the vf in first, so that's going to be natural log of mg minus k vf. And then I'm going to go minus natural log of, and if I put the 0 in, that's going to be natural log of mg. All right. From there, you can do this in a couple of different ways, but probably the easiest way, if you know your natural log rules, if you have this minus that, it's the same thing as natural log of this divided by that, right? And so I'm going to go ahead and do that. So we're going to have TV, that's that final, sorry, not TV, TF, that final time is equal to negative m over k times natural log of mg minus kvf over mg. All right. Now, from there, we're just going to go ahead and solve for v. And hopefully, when we solve for v, we'll be able to get to the final answer. So I'm going to take these, and I'm going to move that over to the other side. Okay, I'm going to go ahead and rewrite it over here. Okay, so I'm going to have negative k t over m equals natural log of mg minus kvf over mg. All right. Then to get rid of the natural log, I'm going to do e to the power of each side. You should have learned how to do that when you were doing logarithms. So it's going to be e to the power of negative kt over m. You'll notice this time it's negative. Remember in the equation last time we said it should have been negative? Depends on the proof. Okay, I looked with Joseph, and we found a proof online where that number was positive, and the proof for that one was exactly the opposite. They defined down as negative and up as positive. So we get this when we're defining the down to be our positive direction. That should then be equal to mg minus k vf over mg. All right, now we will multiply both sides by mg, and then we'll keep going. So multiply both sides by mg, so now we'll have mg e to the negative kt over m equals mg minus k vf. I'll add the mg to the other side, or subtract the mg to the other side, or eventually, I guess, let's do this so that, because we do want our vf to be positive, I'm going to add the k vf to the other side, and I'm going to subtract this one to that side. So I'm going to have k vf equals mg minus mg e to the negative kt over m. And then here, most proofs like this, they're going to take the mg and factor it out, and then they're going to divide by the k. So we'll have vf equals mg over k times 1 minus e to the negative kt over m. So that's what we wanted to get. That's one way to get there. There's multitudes of ways to get there, different kind of integration processes, different ways to kind of think about the process, different simplifications of the algebra, right? Even once we have this down here, different ways to work through there. This is one of many. This is the one that I was most comfortable with, and so this is the one that I am presenting today. All right, now what I want you to recognize is that we now have a formula for final velocity that is dependent on time and K, M, G, which are all constants. K, M, and G are all constants for this situation. So it is unlike the original equation. Remember, in the original equation, we had mg, k, v, but we also had the a, and the a was dependent on v. That was a mess. So therefore, we now have it as a function of time, only as time, and so now we have a function for v. This is essentially v of t, right? So now that we have that, we're going to come back to the board where we have what is expected of you, right? So what is expected of you? Well, I now have a formula, Vf equals mg over k times 1 minus e to the negative kt over m. You do not need to have that memorized. You do not need to have the process of deriving it. That's not expected at this point. It is expected by the end of the year, but it's not expected at this point in time. Now, from here, what do we expect you to be able to do? Well, the first thing that I expect you to be able to do is I expect you to be able to draw a graph using this function and your knowledge of limits to get to a graph of v versus t. So let's start with that. So I've got v and I've got t. So the two things that I want you to be able to think about and to do are, number one, what happens when t equals 0? Okay, so we're looking at the limits. We're looking at some of these important points, sometimes in behavior. These are things you should have learned in your math class. So when t equals 0, that means that this will be e to the 0, which means that is 1, and I'm going to go 1 minus 1, and that's 0. That means this function will be 0. So at t equals 0, v equals 0. Well, that's good, because that's what we said, right? We said the velocity should be 0 at the beginning. Now, secondly, what's the next thing we want to be able to do? Well, I want you to be able to say, as time gets big, as time, not equals, it's not equals, but as time approaches infinity, what do we get? Now, mathematically, they would write out a limit, the limit of this function as t approaches infinity. Well, what happens? Well, as t approaches infinity, this number gets really big. So this is e to a negative big number. That means this becomes 0. And so I have mg over k times 1, which is mg over k. And so therefore, v equals mg over k. That is then my terminal velocity. So I'm going to label mg over k. That's what should happen. I should get closer and closer and closer to that number as t gets bigger and bigger and bigger. Now, that should make sense. If you go back to the equation that we said that you should know and be comfortable with, when acceleration is 0, that's when we get terminal velocity. And if you solve, you add the kv, you divide by k, and you get mg over k is equal to v. And so therefore, we have shown the same thing with the equation. So then, because it's an asymptote, because it's an exponential, I do expect it to look something like this. Okay, now if you're unsure, you can always go into your calculator, you can plug in a couple of points, find out what you get in the middle. But for now, I want you to just have this idea of it's an exponential, therefore it needs to be approaching the asymptote. So something like that. Okay? And of course, as it goes on, it just gets closer and closer and closer to that asymptote. Now, the second thing I want you to be able to do is I want you to be able to do the acceleration. Okay? So we're going to now do an acceleration versus time graph. Now, to do acceleration versus time, you need to take the derivative. Remember, we did talk about the idea that acceleration is dv dt. So I'm going to take this function and I'm going to take the derivative of it. Okay? So if I take the derivative of mg over k times 1 minus e to the negative kt over m. You can do that however you want. I'm going to go ahead and simplify it. I'm going to put the mg over k back in. So I'm going to have mg over k minus mg over k e to the negative kt over m. Now when I take the derivative of this, if this is v, then dv dt, and it does have to be dv dt, that's how you get acceleration. dv dx is not acceleration, that's something else. Okay, dv dt, this is a constant, so that goes away. And then I'll have negative mg over k. The derivative of e to the x is e to the x, but because this has a function inside of there, that's the chain rule, which means I'm going to then have to multiply by the derivative of the inside. And so the derivative of the inside is going to be negative k over m. So I'm going to need to multiply by negative k over m, and then e to the negative kt over m. Now what you'll see is that the negative here is going to cancel out. The m is going to cancel out, and the k is going to cancel out. Now what does that leave us with? Well, that leaves us with acceleration is equal to g times e to the negative kt over m. Sorry, that is a k. Kt over m. All right? Now, same thing as before. When t equals 0, so I'll go, okay, if t equals 0, what do I get? Well, if I put 0 in for t, this is 0. Therefore, e to the 0 power is 1, and acceleration is g. Well, that's good. That's what we said right here, right? At time 0, acceleration was just g. Okay, awesome. So that works. So acceleration is g at that point. Okay, and then what happens when time approaches infinity, when time gets really big? All right, well, when time gets really, really big, this becomes e to the negative really big number. And if I do e to the negative really big number, that is 0. So this is now 0, and 0 times g is 0. And so therefore, the acceleration is 0. Well, that's good because we said the acceleration should be 0, right? And so therefore, I should have an asymptote down here at 0. That as time goes on, as time approaches infinity, I should be getting closer and closer to 0. So therefore, I expect it to look something like this. All right? Now, that should make sense because at the beginning, the slope of v was steep, so I have a large g. That's large A, right? A is the slope of the v graph. Here, v is decreasing, right? The slope is becoming less and less, so therefore, A should be getting less and less and less. In the end, my graph is approaching a slope of 0, and what do I see down here? I see that the value is approaching 0. Not that the slope is approaching 0, that the value is approaching 0. The slope of the velocity versus time graph is acceleration. The slope here is almost 0, therefore the acceleration is almost 0, right? Okay, so we should get this, we should get that, we should get that. Last thing that you should be able to do is this. You should be able to find the displacement, all right? So I'm going to get rid of my acceleration here. And now we're going to create a displacement versus time graph. So same thing, x versus t, all right? And now to get from velocity to displacement, I need to do an integral, right? So again, I'm actually going to take that velocity, which is equal to mg over k minus mg over k e to the negative kt over m. All right. This is not dv, this is the integral. So as I take the integral is going to be with respect to dt. So integral with respect to dt. All right. And when I take the integral of v with respect to time, I get x. All right. The integral of mg over k, that's a constant. The integral of a constant is that constant times t, right? And then I take the integral of mg over k, that is the constant in front of the e to the negative kt over m. Again, if you need it, you can look at your formula sheet. Okay, and if you look right here, it has the integral of e to the ax. Okay, you may not be able to see that, but you should have your formula sheet at home, e to the ax. And we see that if I have e to the a is going to be the negative k over m there. So e to the ax becomes, so I'm going to write minus this mg over k, that stays the same. And then it says I need to do 1 over a. So a is negative k over m. So I'm going to do negative m over k. Okay. Yeah. And then times e to the ax. So e to the negative kt over m. All right. Now that does look a little bit more messy, but it's okay. It's okay. Let's see what we can get when we start to put things in there. Okay, I am going to clean it up just a little bit. All right, so I'm going to go x equals mg over k times t minus, that's going to end up being a plus m over k e to the negative kt over m. So the first question is, what happens as t approaches 0? So if t equals 0, this is 0. If I put 0 up here, that's e to the 0, so that's 1. So I get m over k. And so it's going to be m over k times mg over k. And so when that's 0, I will get m squared g over k squared. All right, so I get some value. All right, that is the value of x. Okay, secondly, I'm going to find out what happens to time as time approaches infinity. Okay, sorry, what happens to x as time approaches infinity? Now, the first thing that you'll notice is that as this gets to infinity, this becomes a really big number. That makes the e 0. That makes this whole term 0. So essentially, that number becomes 0. If that becomes 0, then what I'm left with is mg over k times t. Mg over k times t, that is a linear graph. And so what I recognize is that I'm going to have a linear graph with a slope of mg over k. All right? And so I do expect the x, in the beginning, I have a low velocity. It should be increasing. And then at some point, when I hit my terminal velocity, I'm now going to have a linear graph. Now, that, the slope of that, I should probably just write slope, is equal to mg over k. Because remember, as t approaches infinity, this becomes 0. And so therefore, I just have mg over kt. Now, some of you in the future will look back at this and say, Mr. Bauer, you forgot something. Yes, technically, when I take an integral, I should, because I'm not doing a definite integral here from a to b, I should add on a value at the end. The value that's being added on the end should be our initial x here. And so the actual answer here should be plus x naught. Now, that's not going to make a big difference when we're finding displacement. It will make a difference when we find position, but the actual displacement won't change very much because that x naught will be at the beginning and at the end. And so when we subtract using that definite integral, that will go away anyway. So very often when I'm doing my analysis, I kind of ignore it, which, yeah, I probably shouldn't, but it is what it is. All right. So at this point, we now have some things. These are the things that you should know, you should be comfortable with. You should be able to do the Newton's second law stuff here. You should be able to interpret that. You should be able to take an equation and get the derivative to get the acceleration, and you should be able to get the integral in order to get the displacement. Okay, I think that's it. So I hope that's helpful. I hope that recognizing what is important, what you do need to know now, and what you don't need to know now, what's just kind of extraneous, interesting information, hopefully that's helpful for you. That's the purpose of this video. And hopefully it's a video that you'll go back and look at someday and be like, oh yeah, now I can do that. I got the math now. I can do those integrals. All right. So anyway, hopefully that was helpful, and we'll see you next time.